Big Data Technologies. Introduction to Hadoop. 1. Definition of Hadoop. Hadoop is an open-source framework that allows for the distributed processing of large data sets across clusters of computers using simple programming models. It is designed to scale up from single servers to thousands of machines, each offering local computation and storage. 2. Core components. The core components of Hadoop include HDFS, Hadoop Distributed File System, for storage, Yarn, yet another resource negotiator, for managing computing resources, and MapReduce for processing large data sets. 3. Benefits. Hadoop's major benefits include its ability to store and process huge amounts of any kind of data quickly, massive storage and processing capabilities, and the flexibility to handle limitless concurrent tasks or jobs. 4. Use cases. Hadoop is widely used in industries for applications like big data analytics, data warehousing, data mining, and machine learning. It's particularly effective in processing large, unstructured data sets, such as text and images. Hadoop's architecture and functioning. 1. Distributed storage, HDFS. HDFS stores data across multiple machines without prior organization. It splits large data blocks and distributes them across nodes in a cluster, ensuring high availability and fault tolerance. 2. Distributed processing, MapReduce. MapReduce is a programming model used for processing large data sets with a parallel, distributed algorithm on a cluster. It consists of the map function, for filtering and sorting, and the reduce function, for summarizing data. 3. Resource management, Yarn. Yarn is responsible for managing computing resources in clusters and using them for scheduling users' applications. It improves the scalability and cluster utilization of Hadoop. 4. Scalability and reliability. Hadoop clusters can be easily scaled by adding more nodes. It's designed to be fault tolerant by replicating data across multiple nodes, ensuring high availability and reliability of data. Challenges and solutions in Hadoop. 1. Handling of small files. Hadoop is not efficient for small file storage. A solution is to merge small files into larger ones or use Apache Hbase for better performance with small files. 2. Security concerns. Hadoop's basic security features can be insufficient. Enhanced security can be achieved through Kerberos authentication and Apache Ranger for access control. 3. Complexity and management. Managing a large Hadoop cluster can be complex. Tools like Apache Ambari help in simplifying the management, monitoring, and provisioning of Hadoop clusters. 4. Evolving ecosystem. The Hadoop ecosystem is rapidly evolving, which can be challenging to keep up with. Continuous learning and adapting to new tools and components in the ecosystem is vital for effective use. Understanding Hadoop Distributed File System, HDFS. 1. Definition of HDFS. HDFS is the primary storage system used by Hadoop applications. It is a distributed file system designed to run on commodity hardware and provides high-throughput access to application data. 2. Architecture. HDFS has a master/slave architecture. A typical HDFS cluster consists of a single name node, the master server that manages the file system namespace and controls access to files, and multiple data nodes, which manage storage attached to the nodes that they run on. 3. Data replication. HDFS replicates each data block, typically 128 megabytes in size, across multiple data nodes in the cluster to ensure reliability and fault tolerance. The default replication factor is 3, but it can be configured as needed. 4. Fault tolerance. HDFS is designed to detect and handle failures at the application layer, so it provides fault tolerance and quick recovery. If a data node fails, the data is automatically replicated from other nodes to maintain the replication factor. Key features and benefits of HDFS. 1. High throughput. HDFS provides high throughput access to application data, which is suitable for applications with large data sets. 2. Scalability. HDFS scales well in handling large amounts of data. It supports adding or removing data nodes without interruption to the system. 3. Data locality. HDFS tries to keep the data as close to where it is processed as possible, minimizing network congestion and increasing the overall throughput of the system. 4. Suitability for large files. HDFS is designed to support large files. It provides high bandwidth streaming access to file data, making it suitable for large-scale data processing tasks. Challenges and solutions in HDFS. 1. Balancing of data. One challenge is balancing the data across data nodes. HDFS uses a balancer tool which periodically balances data across the cluster. 2. Small file problem. HDFS is less efficient for small files. A common solution is to combine these into larger files for processing or use a more suitable file system like HBase for small files. 3. Hardware failure. Hardware failure is common. HDFS is designed to continue operating uninterrupted while dealing with failures, by replicating data across different nodes. 4. Backup and recovery. Regular backups and robust disaster recovery strategies are essential. Tools like DistCP, distributed copy, and snapshots can be used for data backup and recovery in HDFS. Understanding MapReduce in Hadoop. 1. Definition of MapReduce. MapReduce is a core component of the Hadoop framework. It's a programming model and processing technique designed to perform large-scale data processing across distributed clusters. 2. How MapReduce works. It works in two phases: the map phase, filters and organizes data, and the reduce phase, performs summary operations. The input data is split into independent chunks processed in parallel. 3. Components of MapReduce. The primary components are Job Tracker, Task Tracker, Mapper, and Reducer. Job Tracker schedules tasks and monitors them. Task Trackers run tasks and report status to Job Tracker. Mapper processes input data, and Reducer aggregates results. 4. Advantages. MapReduce offers high scalability and can process large volumes of data in parallel. It is fault tolerant, ensuring that tasks are re-executed in case of failures, and it's optimized for processing large datasets efficiently. MapReduce workflow and data flow. 1. Input data and splitting. Data is ingested from sources like HDFS and then split into smaller chunks for processing. Each chunk is processed by a separate map task. 2. Map phase. In this phase, each map task processes a chunk of data, performs operations, like filtering, counting, and produces intermediate output in the form of key-value pairs. 3. Shuffle and sort. After the map tasks complete, the intermediate key-value pairs are shuffled and sorted by key. Each unique key and its list of values are then passed to the reducers. 4. Reduce phase. In the reduce phase, each reducer processes the sorted key-value pairs and performs operations like aggregating, summarizing, or filtering data. 5. Output data. The final output of the reduce phase is written back to HDFS or other storage systems. This output can be used for further processing or analysis. Challenges and optimization in MapReduce. 1. Performance tuning. Optimizing performance involves tuning parameters like the number of mappers and reducers, memory allocation, and configuration of the Hadoop cluster. 2. Handling large jobs. Large MapReduce jobs may require careful planning in terms of resource allocation and job scheduling to ensure efficient processing. 3. Data skew and load balancing. Data skew can lead to uneven load across nodes. Techniques like custom partitioning and speculative execution can help balance the load. 4. Integration with other tools. Integrating MapReduce with other Hadoop ecosystem tools like Hive, Pig, and HBase can enhance functionality and ease of use but requires careful configuration and management. Introduction to Yarn in Hadoop. 1. Definition of Yarn. Yarn, yet another resource negotiator, is a resource management layer of Hadoop. It enhances the power of a Hadoop compute cluster by providing a more flexible and efficient way of resource allocation and management. 2. Key components. Yarn consists of the resource manager, node manager, application master, and containers. The resource manager is the master daemon, managing resource allocation. Node managers run on slave machines, managing resource use on each node. The application master negotiates resources from the resource manager and works with the node manager to execute tasks. 3. Functions of Yarn. Yarn decouples the programming model from the resource management infrastructure, leading to improved cluster utilization and increased scalability. It manages computing resources in clusters and uses them for scheduling user applications. 4. Benefits. The primary benefits of Yarn include improved cluster efficiency, better scalability, and support for multiple data processing paradigms besides MapReduce, such as interactive querying and real-time streaming. Yarn architecture and workflow. 1. Resource manager. The resource manager has two main components: the scheduler, which allocates resources based on constraints like capacity, queues, etc., and the application manager, which manages the lifecycle of applications. 2. Node manager. The node manager is a per-node agent responsible for containers, monitoring their resource usage, CPU, memory, disk, network, and reporting the same to the resource manager. 3. Application Master. Each application, like a single MapReduce job, has its own instance of Application Master, which negotiates resources with the resource manager and works with node managers to execute and monitor tasks. 4. Job execution and scheduling. Jobs are submitted to the resource manager, which then forwards them to the appropriate application master. The application master requests containers and executes specific tasks, like MapReduce, on these containers. Challenges and best practices in Yarn. 1. Resource allocation. Effective resource allocation is crucial. It involves configuring Yarn to use available cluster resources optimally, like setting appropriate memory and CPU limits for applications. 2. Scalability. As clusters grow, Yarn must scale accordingly. It's essential to regularly review and adjust resource management settings to handle the increased load. 3. Monitoring and debugging. Regular monitoring of application performance and resource usage is essential for identifying bottlenecks. Tools like Apache Mbari can be used for monitoring and managing Yarn clusters. 4. Integration with other tools. Yarn can be integrated with other Hadoop ecosystem tools like Apache Spark and Hbase. Proper configuration and tuning are required for efficient operation in a Yarn managed cluster. Introduction to Apache Pig. 1. Definition of Apache Pig. Apache Pig is a high-level platform for creating MapReduce programs used with Hadoop. It is designed to simplify the process of working with Hadoop and large data sets by providing an abstraction over MapReduce, reducing the complexity of writing complex Java programs. 2. Key features. Key features include its ability to process large data sets, ease of programming, using Pig Latin, a simple scripting language, and optimization opportunities. Pig scripts are automatically optimized for efficient execution. 3. Pig Latin script. Pig Latin is a high-level scripting language used by Pig. It allows for common data operations like join, filter, group, and sort, and is extensible to support custom functions for more complex data manipulations. 4. Use cases. Apache Pig is ideal for data pipeline creation, ETL, extract, transform, load, operations, iterative data processing, and large-scale data analysis. It's widely used when quick and straightforward solutions are needed for complex data processing tasks. Architecture and components of Apache Pig. 1. Execution modes. Pig can run in 2 modes. Local mode, for running Pig scripts on a single machine, ideal for development and testing, and Hadoop mode, for running scripts on a Hadoop cluster, suitable for processing large datasets. 2. Architecture overview. Pig's architecture consists of the Pig Latin language, a compiler that produces sequences of MapReduce programs, and a runtime environment for executing these programs on a Hadoop cluster. 3. User-defined functions, UDFs. Pig supports UDFs, which allow users to write custom functions in Java, Python, or JavaScript to extend Pig's functionality for specific requirements. 4. Integration with Hadoop ecosystem. Pig integrates seamlessly with the Hadoop ecosystem, including HDFS for storage and Yarn for resource management. It complements other Hadoop tools like Hive and Hbase. Challenges and optimization in Apache Pig. 1. Debugging and error handling. Debugging Pig scripts can be challenging due to the abstraction over MapReduce. It's important to understand the underlying MapReduce execution to effectively debug. 2. Performance tuning. Like MapReduce, Pig jobs can be tuned for better performance. This includes optimizing Pig Latin scripts and configuring resource allocation in the Hadoop cluster. 3. Data types and schema design. Understanding and effectively using Pig's rich set of data types is crucial for efficient script development. Proper schema design can significantly impact performance. 4. Working with large datasets. Handling large datasets requires careful planning in terms of data partitioning and distribution to ensure efficient processing and avoid bottlenecks. Introduction to Apache Hive. 1. Definition of Apache Hive. Apache Hive is a data warehouse software project built on top of Apache Hadoop for providing data query and analysis. It translates SQL-like queries, HiveQL, into MapReduce, Tez, or Spark jobs. 2. Key features. Hive features include its ability to query and manage large datasets residing in distributed storage, support for HiveQL, a SQL-like query language, and integration with Hadoop and other data processing tools. 3. HiveQL. HiveQL is a SQL-like scripting language for querying data in Hive. While it is similar to SQL, it also allows traditional map/reduce programmers to plug in their custom mappers and reducers. 4. Use cases. Apache Hive is primarily used for data summarization, querying, and analysis. It's commonly used in scenarios requiring ad hoc querying, data warehousing, and reporting on large datasets. Architecture and components of Apache Hive. 1. Hive architecture overview. Hive's architecture consists of components like Hive clients, Hive server, Metastore, and execution engine, MapReduce, Tez, or Spark. It processes and analyzes data stored in Hadoop, using HiveQL. 2. Metastore. The Metastore stores metadata about the tables, columns, data types, and HDFS data locations. This information is used by Hive to efficiently process queries. 3. Data storage. Hive stores data in tables. The data files are usually stored in HDFS, Hadoop Distributed File System. Hive also supports other data storage systems like Amazon S3. 4. Hive server and Hive clients. Hive server, HS2, provides a JDBC/ODBC server to connect clients for executing queries. Clients interact with Hive server via interfaces like JDBC, ODBC, or Thrift. Challenges and best practices in Apache Hive. 1. Query optimization. Optimizing Hive queries is critical for performance. This includes understanding and leveraging Hive's query execution plans, indexes, and query vectorization. 2. Data partitioning and bucketing. Efficient data partitioning and bucketing can significantly improve query performance, especially for large datasets. It involves dividing tables into parts based on the value of a column or set of columns. 3. Managing data types. Proper understanding and usage of data types in Hive can prevent data type mismatch and conversion issues, which can impact query performance. 4. Integrating with other tools. Hive integrates with other Hadoop ecosystem components, such as Hibase and Spark. Understanding these integrations is key for maximizing Hive's potential in complex data processing scenarios. File compression techniques in big data. 1. Importance of compression. In big data, file compression is crucial for reducing storage requirements and speeding up data transfer across the network. It helps in optimizing the storage and improving the performance of big data applications. 2. Lossless versus lossy compression. Lossless compression reduces file size without losing any data, for example, zip, snappy, essential for analytical processing. Lossy compression, which discards some data, for example, JPEG and images, is not typically used in big data due to the loss of data integrity. 3. Popular compression formats. Common formats include zip, good compression, but not splittable, snappy, fast compression and decompression, but less compression ratio, zip2, excellent compression, splittable, and LZO, balanced between speed and compression, splittable with indexing. 4. Considerations for choosing compression. Factors include the type of data, the need for splittable files, for parallel processing, compression and decompression speeds, and the compression ratio. The choice depends on whether the priority is on storage space, processing speed, or both. Compression in Hadoop ecosystem. 1. HDFS and compression. HDFS does not inherently compress data, but it supports various compression formats. Compressed files can significantly reduce the amount of storage used in HDFS. 2. MapReduce and compression. MapReduce jobs can read and write data in compressed format. Intermediate data in MapReduce can also be compressed to reduce disk and network I/O. 3. Hive and compression. Hive supports data stored in various compressed formats. Using compressed files in Hive can lead to significant improvements in performance, especially during data loading and querying. 4. Impact on performance. The right compression strategy can improve performance by reducing disk I/O and network bandwidth usage. However, the choice of compression format can impact CPU usage during compression and decompression, so it needs to be balanced based on available resources. Compression best practices in big data. 1. Analyzing data characteristics, understanding the nature of the data, for example, text, binary, structured, unstructured, is key to choosing the appropriate compression format. 2. Compressing intermediate data. In processing frameworks like MapReduce or Spark, compressing intermediate data can lead to significant performance gains. 3. Testing different formats. It's advisable to test different compression formats to find the right balance between compression ratio and the speed of compression/decompression for your specific use case. 4. Monitoring performance. Continuously monitor the performance impact of compression. This includes tracking metrics like CPU usage, disk I/O, and job execution times to ensure that the chosen compression strategy is beneficial. Understanding sequence files in Hadoop. 1. Definition of sequence file. A sequence file is a flat file consisting of binary key/value pairs and is extensively used in Hadoop for MapReduce jobs. It serves as a container to store data in a compressed or uncompressed binary format. 2. Key characteristics. Sequence files are splittable, which allows parallel processing in Hadoop. They support block compression and record compression, and they are suitable for storing a sequence of datasets. 3. Types of sequence files. There are 3 types of sequence files: uncompressed, record compressed, only values are compressed, and block compressed, both keys and values are compressed in blocks. 4. Use cases. Sequence files are used when there is a need to read/write binary data from/ to Hadoop. They are commonly used for intermediate data storage in MapReduce jobs and for storing small files, as a container, to reduce the number of files in HDFS. Advantages and limitations of sequence files. 1. High performance and efficiency. Due to their splittable nature, sequence files allow efficient parallel processing. Their binary format ensures quick read/write operations. 2. Data integrity. Sequence files provide data integrity through checksums for blocks of data. This ensures the reliability of data storage and retrieval. 3. Flexibility and compression. They offer flexibility and compression options, allowing for efficient storage management and faster data processing when using block compression. 4. Limitations. Sequence files are not human readable, making debugging difficult. Also, they are specific to Hadoop, limiting their use in non-Hadoop environments. Working with sequence files. 1. Creating sequence files. Sequence files can be created using Hadoop's API in languages like Java. The developer needs to define key and value classes. 2. Reading sequence files. Reading from sequence files involves using specific readers provided by Hadoop, which can handle the binary format and decompress the data if necessary. 3. Writing to sequence files. Writing to a sequence file requires using writers from Hadoop's API. Data is serialized into binary format and can be optionally compressed. 4. Integration with MapReduce. Sequence files are tightly integrated with MapReduce. They are commonly used as input and output formats in MapReduce jobs for efficient data processing. Thanks for watching.